Hi everyone, here's Bernardo de Souza from FACCTs, and I'm going to present you today some of the new tools we have to build better models. Now, I believe that your calculation is only as good as the model you have when you're trying to reproduce experimental results. So in ORCA we have all these nice calculation methods like coupled cluster and things like that, but we are also working on the direction of how to create better models that represent the experiment, and that's what I'm going to talk about today. It's all very simple, nothing too complicated, so I want to lower the expectation already because it's kind of more or less trivial stuff, but it's helpful, as you will see. So first of all, new tools for more complex models. First of all, the problem of size. So this is FIMOCO. It's a protein with here's 30,000 atoms, and we have 90,000 degrees of freedom. So you need some kind of linear scaling optimizer. Regular optimizer scales n to the power of 3, and they become super slow on this scale already. So we have something called the L-BFGS, which is already used for other mathematical problems with large dimensions like this. And we had something already in ORCA that's called the L-opt. That flag is still the same, but it was redesigned because it needed to be integrated in a rather different way inside the code. And now it's compatible with constraints, it's compatible with everything else that I'm gonna show you today. So it has the same features but more. It also converges in less steps, so it's more efficient than before. And it's integrated with other things like a Docker and Solvator. As I said, what I'm gonna show today, it's all compatible with that. Just to give you an idea, this is a water cluster with 500 water molecules, 1,500 atoms. And the GFNFF energy plus gradient, so the force field energy plus gradient takes about 1 second. And now the L-BFGS Optimizer takes 7 milliseconds. So basically the optimizer contributes to nothing. And if you're working with some force field or something like that, you will notice the difference. It's really significant. And the input is as simple as that. You just have to give L-opt instead of opt, and the linear scaling optimizer will be invoked. This is a nice thing that, as I said, we needed to integrate with other parts of the code. And in the end, we ended up making something that's actually even more efficient. So that was a nice outcome. Something which I really like, and I think that can be explored in many different ways, is this rigid body optimization. So that's a new approach we devised. It's not published anywhere, I think. And the idea is that you can treat any collection of atoms as rigid bodies. So you only allow them to have movements of translation and rotation. And you see this is an example of 2 amino acids, and I use the fragmentator that Nicolas just described. So use autofrag. It will automatically makes 2 fragments out of each of these amino acids. And you can see the optimization is running in a rigid body fashion. So there's no internal movement, there's only rotations and translations. This sounds simple, and it is, but there's more that you can do with that, and I'm going to show that later. Another thing that we have in terms of building models and things like that is the attraction bias. So you can add an arbitrary interaction bias. It looks like this. Let's say you have a water molecule in a gold cluster like that, and you want to have you want the water somehow to be biased to the tip of the pyramid. All that you have to do is to give this bias flag, and then B for bond. It's a bond bias. We only have bond biases now, but we can have more later. And then you give the 2 atoms involved, 20 and 0, and you give you don't need to give, but here I gave a distance of 2 angstrom. Otherwise, it's just the van der Waals distance. And you also can give a strength for the interaction. And here I gave 50 kcal. The default is 25. And when you optimize, like as it's written here, so XTB opt, and then you give the bias, this is what happens. So there is a bias that pushes the water towards the tip of the pyramid. You can define all kinds of arbitrary biases. If you define instead, let's say on the center of the pyramid, then you get something like this. And you essentially are telling ORCA, or you're telling the optimizer, hey, here there's an interaction with a certain distance and a certain strength. Again, sounds relatively simple, but there are several applications for that, and I'm sure you're gonna create even more. What the bias actually is just some potential that has this kind of shape. It's like a Morse, symmetric Morse potential, basically. So it has no wall like a Morse potential, but it's like just some depth where on the potential energy surface where the distance will try to be matched. There's a fifth argument that you can give, which is the steepness. It's just related how flat this surface is. Again, by default, you don't need to give that, only if you really want to. So we also have some improvements for the Docker and for the Solvator. I want to quickly go through that. So the Docker is, if you don't know, the Docker is an algorithm based on swarm intelligence, and the idea is that it finds the way you give molecule A, molecule B, and it will find the best way these two molecules interact. So regular swarm intelligence is a global optimization algorithm. It finds the global minimum of interaction. Here we have a different algorithm that finds multiple local minima. Here you can see on the side you have this molecule, and each of these white balls it could be a solvent, a water molecule. And you can see how the algorithm finds automatically that this white ball, the water molecules, should bind on the left and on the right and on the left, and not in the middle somehow. Right? And that's how ultimately the algorithm works. There are some differences with ORCA 6. So if you have been using this for ORCA 6, please pay attention. The results might differ because they are better now. And it's also about 100 times faster. And I literally mean 100 times faster. So the main difference is that, let me explain that first. So we first we start from some guess, and then we use swarm intelligence to find local minima as shown here. Then we have a pre-optimization step that refines this local minima a little bit, and then we go at the end with some method of choice, like higher level being XTB or something, still semi-empirics, higher method of choice to really find where things bind. The biggest difference here is this pre-optimization method. It was introduced because it really helps in the results. It makes things faster and more accurate. But it's by default based on GFNFF, which is a force field and can fail as everything. So if it fails, you can turn the pre-optimization off, but in the test that I did, it doesn't. So you can go with that. Just to show you some benchmark, this is a benchmark by Christoph Plett and Stefan Grimme on this binding of intermolecular binding of molecules. They also have a more or less similar algorithm for doing this. And these are, as you can see, these are relatively complicated systems. These are not too easy. So you have a Kuurkobieterwiel number A on molecule A with something going in the middle like that. You have this iodine. You have a triple, like C and D are triplets. E, F, and G are metal complexes. And I have here some numbers. So we have the reference results found by CREST. And I have the Docker results. Everything was done on GFN2 XTB potential energy surface. And the time there in minutes. So the time is the time that took for the Docker. Just so you know, the CREST calculations here take hours. So it takes really long to get this interaction energies, and that's how much the Docker needs now. And in ORCA 6, it would have taken also much, much longer than that. There's now you can combine the Docker with these bias potentials, and you can control or at least add a bias for where molecules should interact. So let's say you have this metal complex here, and you have these three positions where you want to make sure you have interactions somehow. You have a carbonyl group, you have two chloride atoms, and if you add a bias, so you just add Docker bias like that, the bias needs to be done in this case inside the Docker, because you have two molecules which are not on the same file. It's all written on the manual, it's very easy to get. And if you add a bias on the carbonyl, then you get the methanol bound, let's say, to the carbonyl. If you use the Solvator, which also uses the Docker on the back. And if you want to bind to the chloride atom, you can also do add a bias. And I mean, this is one structure, but all of them are kind of arranged around the chloride or the carbonyl, because that's the idea. There's a bias now. What you can also do now is you can define a region of space where you want the docking to happen. So here's a protein, and I took the active site, and I defined like a kind of a box and around the active site, and the Docker will only look there. It will not try to bind things on the whole protein. It will just try to bind on the pocket. And to define this pocket, it's very simple. You can either give the coordinates, like XYZ coordinates, or you can give some atoms. This is just some list of atoms. And you take this, then ORCA would take the centroid of those atoms as the center of the grid, and you give a grid extent, and so 10 angstrom here, and you give your guest, and you can dock things into proteins. So this is slow. We're not competing with high throughput docking, But it's also very accurate because there's no scoring function. The scoring function is the total energy of the system here. Just some results to show you. Here's on the left, I just took the ligand out and put it back again. On the right, hemoglobin, I took the heme group out and put that back. There are some people already using it for cases where you have metals and you cannot parameterize force fields, and we have already had the feedback that it's working really well and actually better than most tools out there, which is really nice, and we're going to keep working on that. But now, another feature that I really like, which is this automated coarse graining. So we can combine the fragmentator that Nicolas just presented with the rigid body opt. And that means if you can take a protein like this, you can use the fragmentator to fragment in terms of amino acids. Like you see here, each amino acid has a bubble with a certain color. And you call the rigid body opt and the linear scaling optimizer. And what you get is this. So each amino acid is treated as a rigid body, which effectively means we are coarse graining the GFNFF automatically. So it's a way to take any potential and do some automated coarse graining of that potential, such that in effect you have a coarse grain optimization. This is also, I'm showing you a protein example here. This goes way beyond that, and I'm sure if you're creative, you can figure that out. Here's another relatively smaller example. So terlipressin, it's split into 13 fragments, and you see the optimization running. And you can also see, let's say, that the tyrosine is moving as a whole, and the phenylalanine with the phenyl groups are moving all together. And this really simplifies the dimension of the problem, and this really makes things easier. And of course, the results will be more approximate because everything is constrained, but also it's simpler, faster, and it gets you close to what you want. And then you can just do some fully relaxated optimization afterwards. And that leads us to some improvements to GOAT, which are related to that. So in case you don't know, there's a global optimization algorithm we devised, which is now in ORCA. It's published now in Angewandte this year. So the idea is that you start from some minimum, so like the red ball there, and GOAT will try to push that molecule uphill, try to cross some barrier, and once it detects that the barrier is crossed, it will optimize again, let's say to the blue ball, which might be a new deeper minimum. And it keeps doing that. It creates multiple workers. There's a whole technology there to make this happen, and in the end you get a conformational search algorithm. So here's one example. This is an alanine 10 peptide folding on the GFN2 XTB potential energy surface. And you can see that it in the end, it looks like some kind of artificial intelligence, right? But it's not. It's just very, very classical stuff going on here. And you can now combine that with the rigid body and the automatic fragmentation, and you can have a coarse-grained GOAT, which means it's a global optimization that but GOAT will only move things as blocks. So here's the alanine 10. On the top, you can see if you do this fragmentation procedure called functional groups, it will split the whole peptide into functional groups, as each fragment can be seen there. And these fragments are moving as rigid bodies. So every methyl group moves as a rigid body. Every carbonyl, every NH, every CH, and so on. And again, for a problem that scales exponentially, like global optimization, this really, really saves some time. So instead of 100 atoms, you effectively have 40 atoms or 40 fragments in the end. And then GOAT coarse takes this into account and calculates the number of steps that you need and can give you some results. Again, they will be less accurate, but it will be much faster, and you can get close to the global minimum first. And it's like you can use it as kind of a pre-screening method. So just some examples, like alanine 10 goes from 100 atoms to 40 fragments. So that's a difference of, that's the difference in number of atoms, but effectively the number of geometry optimizations that you need to do is reduced by a factor of 4. So from 4,000 to 1,000. The PAC, it's a pacritinib, that's a drug. It goes from 60 atoms to 20 fragments, and you have a factor of 5, and this is phenylalanine 2, so a dipeptide, and you have a factor of 7. So you go from 500 optimizations to 80 something, so much less optimizations. Of course, again, this will be less accurate naturally. This is the error of the global energy conformer found using the coarse-grained approach versus the full approach. but still it gets you relatively or close enough so that you can then do some other calculation on top. We're still working further on that, but that's what you can do right now. And there's another option I want to finalize, which is called goat diversity. The idea is here to not take into, so it's to do the conformer search, but not to find the global minimum necessarily, but create regions so to find a set of most diverse possible ensemble. So basically what we do is we create an RMSD excluding radius. So you find a conformer and you exclude all conformers that have a certain RMSD around that. This is very useful when your potential energy surface, when you do this, in which you do the search, is bad anyways. Let's say you have a metal complex or something, and you know that GGFN2 is not good for that, and you need to re-optimize anyway afterwards. Then it's, instead of trying to find the global minimum on a potential energy surface, which is wrong, it's sometimes better to just spread it all over, try to find as much conformers as you can, which are geometrically diverse, and hope that these will fall into the global minimum when you switch potential energy surfaces. All you have to do to use that is to set goat diversity, and if you can control the RMSD by giving it under goat. So this is just the example of the alanine 10. If you run a regular goat run, you get basically everything like a blob, like the lowest energy and everything around that more or less. But in the goat diversity, you even got the fully stretched structure, as you can see, because it really tries to find geometric diversity. Here's another example of a metal complex. And again, you find structures which are relatively different in energy and also different in RMSD. And the average RMSD between all pairs for this metal complex was about 4.5 angstrom. And since it's a silver complex, it's relatively, there's a phosphine, it's not likely that some cheaper method will get the right energies. And in this case, it's better to just do a very, very spread out diverse search and then look for the best minimum. And that's it. I hope you can enjoy this. If you are creative, I guarantee there's a lot you can take out of that. We are working on more things in this direction, but it's not ready yet. So I'm Bernardo. If you need, you can contact me. And yeah, happy to hear from questions from you. Bye-bye.